Good morning, class. Welcome to the continuation of our probability and statistics class about estimation of parameters. For today, we're going to discuss lesson 5. Computing interval estimates of population proportions. Our objectives are first, identify the appropriate form of the confidence interval estimator for the population proportion. Second, compute the interval estimates of population proportions. And lastly, solve problems involving confidence interval estimation of the population proportion. So it has been a common practice to obtain data using surveys as basis of our decision making. So almost every day we hear news media reports results of some poll. How are conclusions made from count data? There are systematic procedures in statistics in order to make sense out of this frequency. So we will learn about more of this in this lesson. So as with the estimates of the population mean, we want to ensure that our estimates based on samples contain the true value of the population proportion. So can we think of a way of doing this? Just like the means, we can also form confidence intervals about the population P in a manner analogous to the used for the estimation of the population parameter mu. Okay, we can also assign a probability that the interval contains the population proportion. So the interval depends on the sampling distribution of your p hat. That is, if we were to draw random samples over and over again, each time calculating a new estimate p hat, then the frequency distribution of all the p hat values would be p. Thus, the p hat is an unbiased estimator of p. So we can recall that the standard deviation of the sampling distribution of p hat is given by this. So we have this formula if you remember. So the margin of error for the confidence interval of a population proportion will be this one. Okay? So that the formula for computing a large sample confidence interval for a population proportion will be this one. So we're going to use it later in our example. So the following assumptions are made for finding a confidence interval for a population proportion. So first, the sample is a random sample. Second, the condition for a binomial experiment are satisfied. So let's have an example for this. A survey of 1,200 citizens showed that 715 trust the president. Compute a 95% confidence interval for the proportion of all citizens who trust the president. To solve this, we're going to recall the four-step method in estimating a population parameter. So first, we're going to find the point estimates and we're going to describe the population parameter of the interest. So based on our sample statement, so the parameter of interest is the mean proportion of P of all citizens who trust the president. Second, we need to specify the confidence interval criteria. First, we need to check the assumption. So, by the central limit theorem, the sample size of 1,200 citizens is normally distributed. And next, we're going to determine the test statistics to be used to calculate the interval. And the test statistic for this is the P. Lastly, we're going to state the level of the confidence, which is 95% and an alpha of 0.05. So therefore, your confidence coefficients based on your Z table or Z value, that will be positive, negative 1.96. Third step is we're going to collect and present sample evidences. So first, we're going to collect the sample information. So that will be X, or your random sample is equal to 715 and Your sample size n is equal to 1,200. And last, we're going to find the point estimate. So, since this is a population proportion, we're going to use the p of hat is equal to your x over n. So, substitute this. 715 divided by 1,200, that will be 0.59595, or round this off to two decimal places, that will be 0.60. We're going to find the 95% confidence interval. So we're done with your point estimate. So for this, we're going to compute the interval estimate. So first, we're going to find the Q hat. And to find the Q hat, that will be equal to 1 minus your P hat. So 1 minus 0.60, that will be 0.40. Okay, so next steps, substitute the value of n to your q hat in the formula to find the maximum error of the estimate. So this will be our formula, the square root of your p hat times times your q hat over your sample size n. So substitute this, that will be 0.60 multiplied by 0.4 over 1,200. Square root of 0.24 over 1,200. So it will give us square root of 0.002, which is equal to 0.014, and so on. So okay, so you can continue this in your calculator. Okay, next we're going to find the limits, the lower and the upper limit. So this will be our formula. Okay, let's substitute. Your p hat is 0.6 plus your maximum error, that will be minus 1.96, multiply by the this one, that is will be 0.014, that. So there's the decimal numbers here. Okay, so 0.60 minus 0.0277, so equals 0.573, or convert this to percentage, that is 57.3%. So this is your lower limit. Now let's have the upper limit. So 0.60 plus 1.96 multiply by 0.014, okay? So 0.60 plus 0.027, so it could give us an answer of 0.627. Convert this to percentage, that is 62.7%. So this will be the upper limit. So therefore, we can say that with 95% confidence, we can state that interval from 57.3% to 62.7% contains the true percentage of all citizens who trust the president. We're now on our lesson 6, which is interpreting interval estimate of a population proportion. So our objectives are: first, compute interval estimate of a population proportion. Second, interpret results of interval estimate of a population proportion. And lastly, solve problems involving population proportion. So there are certain issues in society that require sufficient evidence for decision making. For example, should the use of marijuana be legalized? To find an answer to this question, you will have to conduct a survey to a sufficient sample of the public, then calculate and interpret the population portion and present the results to the lawmakers as possible reference for policy information. So in this lesson, we shall look at the interpretation of the results of interval estimation of population parameters. Statistical analysis of numerical data includes an end-node code interpretation. So after computing pertinent values, we make sense out of the entire exercise, so entire activity. The interpretation is important as it provides the reason or impetus for action like improving practices so based on our sample information. So let's have an example for this. So in a teacher college, a survey was conducted to determine the proportion of students who want to major in science. If 368 out of 850 students said yes with 95% confidence, what interpretation can we make regarding the probability that all students in the teacher graduate college want to major in science? In finding the point estimate, we need first to describe the population parameter of interest. And according to this example or question, the parameter of interest is the mean proportion P of all students in the teacher graduate college who want to major in science. Second, we need to specify the confidence interval criteria. Under that, we need to check the assumptions. So by the central limit theorem, the sample size of 850 is normally distributed. And we need to determine also the test statistics to be used to calculate the interval. And for this question, the test statistics is P. Lastly, the level confidence. We need to state the level of confidence. Confidence level is 95%, wherein its alpha is 0.05 and its confidence coefficients are positive, negative 1.96. So for our third step, we need to collect and present sample evidence. So the sample information is your random variable of 368 and your sample size n of 850. Lastly, we need to find the point estimate of p, and to find that, we'll be using this formula that is p hat is equal to your x over the sample size n. So that will be 368 divided by 850. So it will give us a sum of 0.43432, or round this off, that will be 0.43. So therefore, the point estimate of the population proportion is 43%. We're now going to find the 95% confidence interval. So for our first step or our fourth step, that is to compute the interval estimate. So under that, we need to find the Q hat. And to find the Q hat, we have this formula, that is Q hat is equal to your 1 minus your p hat. So that will be 1 minus 0.43. And the answer will be 0.57. So next, we're going to substitute the value of n in the formula to find the maximum error of estimate. And the formula will be square root of your p hat multiplied by your q hat over the sample size n. And if we substitute this, the value of our p hat is 0.43. And for the q hat, that is 0.57 divided by 850. Therefore, it will give us a square root of 0.000288. And if we square root this number, the answer would be 0.0167 and so on. So we round this off to the three decimal places. Okay, so next step, we're going to find the limits. So first, we're going to find the lower limits. And the formula for that is p hat minus your say sub alpha over 2 times the square root of your p hat multiplied by your q hat over n. So if we substitute this, that will be 0.43 minus 1.96 multiplied by 0.017. So that will be 0.43 minus 0.034. It will give us an answer of 0.396 or 39.6. So this is your lower limits. And to find the upper limit, that is p hat plus z sub alpha over 2 square root of your p hat times the q hat over n. So substituting the value 0.43 plus 1.96 multiply by 0.017. So 0.43 plus 0.034, it will give us an answer of 0.464 or 46.4%. So our results will be with 95% confidence. We can assert that the interval from 39.6% to 46.4% contains the true percentage of all graduate students who want to major in science. We're now on our last lesson, lesson 7, all about confidence level and sample size. So, our objectives are first, understand the relationship of confidence interval to sample size, and determine sample size based on selected confidence level. So, we would question ourselves, how large should a sample be? How many researchers find this a problem? So, in fact, many rely on old methods to determine the sample size they need in their investigations. So, this problem should be addressed carefully because, needlessly, large samples are a waste of important resources. On the other hand, insufficient sample size may lead to your poor results. So, there are two things to remember when we decide on the quality of the sample size we need. So, first, the confidence and the narrowness of the interval. So, the computing formula in determining sample size is derived from the formula of the margin of error E. So, if you remember that, we have E is equal to your say sub alpha over 2 times the standard deviation over the square root of your sample size n. Therefore, the formula in determining the minimum sample size needed when estimating the population mean is derived from the margin error formula. So this will be our formula for that. So n is equal to your say sub alpha over 2 multiply by your standard deviation over e or your margin error and then square root. Okay, let's have an example for this. So in a certain village, Leonie wants to estimate the mean weight mu in kilograms of all 6-year-old children to be included in feeding program. She wants to be 99% confident that the estimate of mu or mean is accurate to within 0.06 kilogram. Suppose from a previous study, the standard deviation of the weights of the target population was 0.05. What should the sample size be? Let us first identify what are your given. So we have confidence level of 99%. Then that will be alpha is equal to your 1 minus 0.05. 99, which is equal to 0.01. So the phrase accurate to within 0.06 kilogram indicates that we have a narrow width of the confidence interval. So we can say that desired error is 0.06. By the way, your confidence coefficient or your Z sub alpha over 2 is equal to positive negative 2.58. So the population standard deviation would be zero point 0.5 kilograms. And the formula that we're going to use will be here. Therefore, substituting the values, that will be 2.58 multiplied by 0.5 over 0.06 squared. Okay? So it will give us an answer of 1.29 over 0.06 squared. So 21.5 squared, that will be equal to 462.25. So for this, we're going to round the value to 460. So the required sample size is, conclusion, required sample size is 463 6-year-old children. Next, the formula in determining the minimum sample size needed when estimating the population proportion will be here. So that is n is equal to your p hat multiplied by your q hat times your confidence coefficient, or say sub alpha over 2 over your margin error of e, and then squared. So in computing the sample size for estimating a population proportion, there are two situations to bear in mind. So first, if some approximations of p is known, the value may be used in the formula. So if no approximation is known, use p hat is equal to 0.5. So this value will result in a sample size large enough to guarantee prediction given the confidence interval and the error of estimate. The reason is that when P hat and Q hat are zero point 0.5 each, the product is at maximum. Also, there are steps in solving for sample size involving proportion. First, we need to determine the confidence level. Second, determine the confidence coefficients. Third, determine the error E. Fourth, determine the P hat and Q hat. Lastly, and fifth, substitute the values in the formula of this. 6. Round up the resulting value to the nearest whole number. Okay, let's have an example. So Mary wants to know with 95% confidence the proportion of household who like to use detergent X. A previous survey showed that 42% like to use detergent X. Mary likes to be accurate with 2% of the true proportion. What sample size does Mary needed? Based on the question, our computing formula would be n is equal to your p hat multiplied by your q hat times z sub alpha over 2 over e squared. Okay, so the error e is pegged at 2%. So your p hat is equal to 0.42 or 42%. And to find the q hat, that will be 1 minus 0.42, which is equal to 0.58. So first, let's also determine the confidence level, which is 95%. Then, after we determine the confidence level, we need to determine the confidence coefficient. And That will be 1.96. By the way, your alpha would be 0.05. Okay, so next, since we have all this given, we need to substitute the values in this formula. So that will be 0.42 multiplied by 0.58 times 1.96 over 0.02 squared. So 0.42 times 0.58 multiply by 9,604. So the product of this will be 200 by 2,339.53. If we round this off to a whole number, that will be n is equal to 2,340. So therefore, Mary needs a sample of 2,340 respondents. Congratulations, class. We're done with our chapter 4 topic for the probability and statistics class, which is the estimation of parameters. So I hope you've learned a lot. And before we leave, according to Anne Frank, whoever is happy will make others happy too. Okay. I hope you enjoy our lesson and see you on our next class. Bye!